Section 4.9, Static and Kinetic Frictional Forces. So when an object is in contact with a surface, there's a force acting on that object. We've already seen that there's a component perpendicular to the surface, and that's our normal force. The component of the force that is parallel to the surface is called the frictional force. So we tend to just focus on the specific subdivisions of them instead of trying to combine them into one force, but we focus on the normal force and the frictional force, which we'll see is static and kinetic. And this emerges from the contact points between the object. This is at the microscopic scale, but there are these points of contact that are rubbing against each other, even with objects that appear very, very smooth. So let's take a look at when two surfaces are not sliding across another. This is called static friction. This is illustrated very nicely by this comic, which shows a library with a friction section and a non-friction section, right? With the friction section, the books are able to nicely stay on the shelf. Friction is holding them in place. The non-friction, they're not able to stay on the shelf. They slip right off. So static friction is all around us. It's something we actually take for granted. And it's pretty powerful. It ends up being pretty helpful. So that's shown here with the block and tugging on the block, right? And so pulling some force, and the block might not move right away, right? Or you can try this out with your book, right? If you push on it a little, it might not actually move, but I'm exerting a force. Why is it not moving? Well, it's because of this static frictional force, which we note with a lowercase f and a subscript of an s for static friction, that's acting to oppose the force. So if I'm trying to push my book one way, this force of static friction is acting the opposite direction. You can even push with a larger amount of force, and the force of static friction will similarly get larger to match your applied force, up to a certain point, right? If I push hard enough, my book will start to slide and slide off my hand, which is dangerous. Or the block here will just start to slide once the force of static friction reaches some maximum value. So that's the key with static friction. So it turns out it can take on a range of values up to a maximum value. And that's what's shown mathematically here, that the magnitude of the static frictional force can have any value from 0 all the way up to this Fs max, the maximum static friction value. And this in practice is the one that we will often calculate, Fs max, because we can calculate with mu sub s times the normal force, right? Once again, this is not the net force, but the normal force. So just want to write that. What is this mu sub s? Well, mu is a Greek letter, and it has the subscript s, so it's known as the coefficient of static friction. And it will always be greater than or equal to 0. If there's absolutely no friction, then the coefficient of static friction is 0. In most cases, there's a minuscule amount of it, or perhaps a very large amount of it, so it can get significantly larger than 0. But this shows how we can calculate the maximum value of the static friction. It can go up to this value of the coefficient of static friction times the normal force. Note, this is not a vector equation. So the force of static friction is not in the same direction as the normal force. In fact, they will always be perpendicular to each other. So you have to fill in the direction of the static frictional force to oppose whatever force is acting on it. One interesting note is that the magnitude of the frictional force does not depend on the contact area of the surfaces. So if you have the same block or book, right, and you have it with different orientations, all 3 of these orientations are going to have the same amount of friction. Even though one of them, say, has more area in contact with the surface, it also has less mass pushing down on each of those small area points, versus the one that has less area has more mass on each of those points. So it all balances out is the short of it. And all that we have to worry about is how much normal force there is between these two objects and then the coefficient of static friction, which is something that's either given to us or we can look up in a table. So that's our static friction that occurs when things are static or not moving. And it is going to oppose the impending relative motion between two objects. So you have to figure out, like, okay, if there was no friction, which way would the objects move? What way would they want to go? And for static frictional force, it's going to be in the opposite direction, right? So if I have my book again and say it's on a slope, if there was no friction between my hand and the book would slide right down, right? It would get out of my hand. So there must be friction that's acting up along this slope in order to keep the book there. So parallel to the surface between my hand and the book itself. Now, kinetic friction opposes the relative sliding motion that actually does occur, right? So this isn't just impending or potentially could occur. It's like, okay, my book is now sliding, right? So if it's sliding one way or the other, what's the direction of the kinetic friction? Well, it's just against the sliding. And we can calculate the magnitude of it with an equation that looks remarkably similar to that of our static friction, right? It's the normal force times another coefficient. The only difference is this is going to be the coefficient of kinetic friction, which is different than our mu sub s, the coefficient of static friction. Turns out they have very different values. So let's take a look at some of the values. So here's a table in the coefficient of static friction, the coefficient of kinetic friction. These coefficients, by the way, are always experimentally determined for two materials. So it's something, like I said, that has to be given to you either in a table or in the problem statement. All right, so we could have glass on glass dry. The coefficient of static friction is 0.94. Kinetic friction is half that, 0.4. Right? We could ice on ice. That's roughly frictionless, right? Well, it's much less friction. Static friction's coefficient is 0.1. The coefficient of kinetic friction, 0.02. So that's pretty remarkable. There's very little kinetic friction when you have ice on ice. The other thing to note here is that with each of these, except for perhaps Teflon on Teflon, the coefficient of kinetic friction is significantly smaller than the coefficient of static friction. And this illustrates another thing you may have observed before without really knowing why. Why is it harder to get an object moving? Or why is it easier to push on an object once it's already moving? Well, to get it moving, you have to overcome this static frictional force, in which it turns out the max static friction is larger than the force of kinetic friction. So if you can just get something moving, you'll have less friction opposing your force. Pretty cool. All right. So with this in mind, you can look at an example where there's, say, someone on a sled, and they're moving with some pretty good speed, 4 meters per second, but after some distance, they stop. Why do they stop? Well, there's this kinetic frictional force that opposes the motion of the sled and causes the sled to slow down until it stops. Once the sled stops, there's no more kinetic friction because it's not moving. So if we wanted to draw a free body diagram of this, we would draw our weight as before, mg down, the normal force, which is the surface of the ground pushing up on the sled so that the sled isn't sinking through the earth. And now we're going to add in the force of kinetic friction that is acting opposite the velocity of the sled in the negative x direction in this instance. So let's look at a mathematical example here. Suppose the coefficient of kinetic friction between the sled and snow is 0.05. The total mass of the sled and rider is 40 kilograms. What is the kinetic frictional force? So how can we find the magnitude of this force? We figured out the direction. It's in the negative x direction, but what about getting the magnitude of it? Well, for that, we can just go to our equation for F sub k, right? The magnitude of F sub k is equal to the coefficient mu sub k of kinetic friction times the normal force. Now, in this instance, for the normal force, we note that it is opposed only by the weight of the sled and rider, right? So in this instance, if we look at the forces in the vertical direction, we would find that the normal force is equal to the weight of the sled and the rider, mg. This won't be true in every instance, so you want to understand where that came from. It came from the free body diagram. So this isn't a general equation that you can apply to every scenario. Versus the force of kinetic friction, this one is a general equation. All right, so with those notes, we can go ahead and calculate the force of kinetic friction with our equation, plugging in mg for the normal force. And then we just have our coefficient 0.05 times the mass, 40 kilograms, times g, positive 9.8 meters per second squared. Remember, little g is always a positive number. If you need it to be negative, you have to deal with the negative outside of the equation. So this comes out to 20 newtons of our kinetic frictional force. And once you know that net force that is acting in the x direction, you could then actually take it one step further and find the acceleration that the sled experiences as it slows to a stop. And you could relate that to the two speeds to even solve for the distance that the sled requires to stop. But I'll leave that to you to think about. I'm happy to discuss it further if you are interested, but this is sufficient to introduce our understanding of static and kinetic frictional forces.